All right, so now we're going to look at 26218, special provisions for motor circuit capacitors. So here I've got two pictures. So we can do power factor correction right on the motor branch circuit. And there's two spots where to hook up the capacitor. On the load side of the disconnecting means here, and this is also on the load side of the disconnecting means, but the difference is, in this one is the load side of the motor controller. It's on the load side of the overloads. That's the key here. And here, it's on the line side of the overloads. All right, so let's read the rules, and we've got to be aware of what's happening here. So 26218 subrule 1 applies here, and it also applies here. Where a capacitor is connected on the load side of a motor circuit disconnecting means, an individual disconnecting means for the capacitor need not be provided. The rating of the disconnecting means, the overcurrent device, and the size of the motor circuit conductors need not be greater than would be required without the capacitor. And C, the ampacity of the conductors connecting the capacitor to the motor circuit shall be in accordance with 26208 and shall not be less than 1/3 that of the motor circuit conductors. All right, so what they're saying here, you size the motor circuit conductors as if the capacitor wasn't there. You don't change anything. Then, when I do connect the capacitor up, these conductors have to be at least 1/3 that of the motor branch circuit conductors. All right? That's subrule 1A, B, and C. So it applies here, and it applies here. Then subrule 2. Where a capacitor is connected on the load side of the motor controller. So this is what you got to be aware of. They're on the load side of the overloads. So when we do power factor correction with a capacitor on a motor branch circuit like this, we're reducing the current. All right? The capacitor and the inductor, which is the motor, just start juggling current back and forth. So in this case, we've got a reduction of the line current here, and the capacitor and the motor are simply juggling current back and forth here, but it's all going through the overload. Here, when I have the capacitor connected up on the load side of the overload, we get a reduction of current through the overload. So we have to downsize the overload here, all right? But we have to read on because there's some unique things about this method that we got to be aware of. It says, where a capacitor is connected on the load side of a motor controller, the rating of the capacitor shall not exceed the value to raise the no-load power factor of the motor to unity. So manufacturers have capacitor power factor correction capacitor charts for selecting them for motor horsepower. So that's a statement really for engineers on design. You don't have to worry about it. You're not going to have to size the capacitor. They're just making you aware of that. B, the rating or setting of the overload device shall be reduced to a value corresponding to the current obtained with the improved power factor. So now this capacitor is going to reduce the current through the overload here. We must reduce the size of the overload setting. Here, the capacitor still gets to see the full motor current. C, individual overcurrent protection for the capacitor need not be provided, because we're going to use this fuse here on the motor that's going to do power factor correction, or sorry, it's going to do overcurrent protection for the capacitor and the motor at the same time. The motor shall not be subject to star delta starting, auto transformer starting, or switching service such as plugging, rapid reversals, reclosings, jogging, or other similar operations that generate over voltages and over torques. And E, Time delay fuses shall be installed in the motor control circuit of motors driving high inertia loads so that the motor cannot be restarted until the residual voltage is reduced to 10% of the nominal voltage. All right, so you fourth year guys, in your exercise book, there's an example of this. If you listen to this explanation, you should be able to handle the question. Now, some people get confused as well. I've got a capacitor and a motor here. They're both loads. How does this fuse hold both loads? Well, you got to understand the difference between an inductor and a capacitor. One's only drawing current at one time, right? Because they're opposite from each other. They're 180 degrees out of phase. When this is discharging, the motor's drawing current. When this is discharging, right, they're opposite, and we get a reduction in line current. So the fuse will work there. All right. The drainage of stored charge now, you guys. This here and this here, two different spots. This is also on the line side of the contactor. This is on the load side of the contactor. Here, I can use the motor for a suitable discharge path. It can discharge right through the motor. Here, we have to provide that discharge path. This is what I was mentioning in the other earlier video. That on subrule 5, 26222 subrule 5, motors, transformers, and other electrical equipment capable of constituting a suitable discharge path connected directly to capacitors without the interposition of a switch or overcurrent device shall be considered to constitute a suitable discharge path. That applies there. That's a switch, right? We're switching the motor on and off there with the contactor. It doesn't apply there. All right? So know when and where, or understand that. All right. That takes care of all the capacitor things that you could possibly get hit with. Year 2, single phase. Year 3, three-phase and single phase. And year 4 and 3, this motor 1 power factor correction with a capacitor. All right, we'll see you then.